right, in this section we are going to talk about theoretical probabilities. Theoretical probabilities are probabilities that do not require that you do an experiment of any kind in order to find the probability of something happening. So for example, if I was going to ask you to, reach into a bag of M&Ms and tell me the probability you pulled out a yellow one, well, you're not going to be able to figure that out unless you know how many M&Ms are in the bag and how many of them are yellow. Okay, you're going to have to calculate that probability first, then you would know. Okay, those are not equally likely outcomes. M&Ms are not equally distributed in terms of color. Theoretical probability are probabilities you can do without doing an experiment. Okay, so theoretical probabilities can be found without doing an experiment. Okay, so one such example we can find the probability of rolling doubles on a pair of dice by finding the number of outcomes that are doubles divided by the number of outcomes in S, the sample space. Okay, so that little n just means the number of, okay, number of doubles and the number of things in S. Remember, we denoted the sample space as S. If you'll remember from the previous section, there were 6 different ways we could get doubles, 1, 1, 2, 2, 3, 3, etc. And there were 36 possible outcomes for a probability of 1/6. Okay, one important note to make here is if you're going to find theoretical probability, we must have equally likely outcomes. In order to find theoretical probability. And I'm just gonna finish that up there. Okay, equally likely outcomes, all right? In other words, everything has to have the same chance as every other outcome. All right, so some general rules here for probability, okay? Things that will always be true. So the probability of an impossible event, we'll call it X, okay, meaning whatever it is. If that event is impossible, then the probability of X happening is 0, okay? It's not going to happen. The probability of a certain event. Now, certain is not like specific, that one over there, that particular one. Here, certain is the term guaranteed. Okay, like I am absolutely certain that today is Tuesday or whatever. Okay, so guaranteed. All right, guaranteed. The probability of an absolutely 100% guaranteed event is 100%, but we're going to say 1 because we will give our probabilities as decimal forms of numbers, not percentages. Okay. The sum of the probabilities of all the outcomes. Okay, so I'm going to use our summation notation again. So the sum of all probabilities of all the outcomes, whatever all those are, have to add up to 1 or 100% of the time. Okay, and for any event, no matter what it is, the probability of that event has to be between 0 and 1 inclusive. So if you calculate a probability and you get a negative answer, that's wrong. And if you calculate a probability and you get an answer bigger than 1, it's wrong. Okay, I don't know what you've done wrong necessarily, but I can definitely tell you it's wrong, and you should make note of the fact that it's definitely wrong as well. Okay, your answers have to be between 0 and 1. All right. So use the table in example 2 on page 2. So just flip back 1 page in your notes to calculate the probability of not buying a Toyota. Okay, well, if you look back, the probability of buying a Toyota was 0.088. Okay, so the probability of getting a Toyota is 0.088. So what's the probability of not buying a Toyota? Okay, how would we do that? Well, if the sum of all the probabilities is 1, right, we should add up all the others, or add them all together and we should get 1. We can take 1 minus the probability we have a Toyota to get the overall probability of not buying a Toyota, which would be 0.912. The alternative would be to add up the probability of all the other types of cars, okay? But this way is definitely faster. It also leads us to the definition of complement, okay? So we're going to define the complement of an event, and I'm going to give you some notation as well, all right? So the complement, spelled different than like, ooh, don't you look nice today? That's compliment with an I, M-E-N-T. But the complement of some event, which we're going to call capital E, is the list of outcomes that are not in E. Okay, all the things that are not in E. So when it said not a Toyota, that meant all of the things that were Ford, Honda, GM, or Mazda in the previous example. Okay, notation for complement. I'm going to write them in the order in which you will let me just trip over my words a little bit, typically see them, okay? The one you're going to see the most in this course is E with like a superscript C, okay? E complement, that's the one we're going to use the most. You will also see these two occasionally. You'll see an E with a bar across the top. That's not E bar, like we have X bar, that's E complement. And you'll also see E with a prime, which also means complement. But again, for our purposes in this class, I'm going to stick with this one for notes, but that does not mean in some of the online homework, you occasionally won't see the other notations because other people do use those. It's really a matter of personal preference. Okay. Now, as for the complement rule, what in the heck is that? Well, since the probability of an event happening plus the probability of the complement of that event happening, so the event happening and the event not happening equals 1, we can say that the probability of the complement of an event is 1 minus the probability of the event. Okay, so the probability of the complement of an event, a not, is 1 minus the probability of that event. And again, there's a lot of common sense there. All that says is the exact same thing we did in example 1, just in generic math speak instead of in concrete example form.